Today's lesson deals with an introduction to the quantum mechanical model of the atom. So let's begin with a brief history lesson and remember what our earlier models about the atom had looked like. So early on, Rutherford, he was the first one to identify the nucleus, where he said we had a concentration of all our positively charged particles. And most of the atom was empty space, with the negatively charged electron particles scattered around the nucleus. Then Niels Bohr makes some adjustments to the Rutherford model. He actually had been working with Rutherford at one point. He's agreed that the mass of the atom was in the nucleus, concentrated there. But instead of just being randomly scattered around this nucleus, he saw the electrons as moving in a fixed, definite circular path, which he called an orbit. And these orbits were at fixed distances from the nucleus based on the amount of energy that they had, and that the electron could gain or lose energy. So it looked much like the way we envision our solar system, with the sun at the center and the planets circling the sun. He saw the nucleus at the center with the electrons circling the nucleus in fixed orbits. Bohr's model however, was somewhat limited in trying to explain some of the spectral lines that we observed on elements beyond hydrogen. And it was de Broglie who recognized some of the problem was that electrons are not just behaving like mass particles, but they are also having properties of waves, which is energy. So they are behaving like both matter and energy. And the reason he believed this was because there was experimental evidence to actually support this. So a mathematician, Schrödinger, comes along and develops actual equations, wave functions, that are able to describe this motion of the electrons behaving as both particles and waves. And as a result, our model, instead of being fixed orbits around the nucleus, we get this idea of an electron cloud. From this, our very complex quantum mechanical theory is born. It's a result of many scientists, in particular Schrödinger, Heisenberg, and Einstein. And it is a result of the Schrödinger equation that we are able to assign values to help us figure out where an electron is. And we are not going to be able to tell you exactly where the electron is, but most likely where it is. So we're going to see that the Bohr orbits, which we said were fixed circular paths around the nucleus, are being replaced with what we call quantum mechanical orbitals. So don't be confused by the similarity of the two words. An orbit means it was a fixed location, just like our planets revolving around the sun in a fixed path. The orbital means it's a probable location, that it is a probability map where I'm most likely going to find it, and it gives us this idea of a fuzzy electron cloud. So notice the difference in our model here shown at the bottom, where instead of having defined paths, we have these fuzzy areas. So the electron is most likely here at one energy level. Now, the Schrödinger equation is extremely complex, and we're not going to make any effort to try and understand or use those values here in class, but we're going to use a simplified idea that results, and we find that every electron can be described by 4 quantum numbers. And if I know those 4 quantum numbers, I can give you the most probable location for a particular electron of an element. It's sort of like using a GPS, but instead of it getting you exactly to someone's front door, it gets you in the neighborhood. So what are these 4 quantum numbers? So the first one is the principal quantum number, and that is going to tell us really how far we are from the nucleus. It tells us the energy level, which, if you remember, means it's getting you to the period on your periodic table. Then we have the angular number. That's going to describe the shape of the orbital. Then we have the magnetic quantum number, which gives you the orbital's orientation in space, so sort of its axes. And finally, we have the spin number, which tells you whether the electron is spinning clockwise or counterclockwise. And here is a picture trying to illustrate what the different quantum numbers are telling us. Our first quantum number, represented by the letter n, the principal quantum number, is going to tell us the size of the electron cloud. So is that cloud very close to the nucleus, or is it further away? That's really all that that first number is telling us. So when we're describing the electron cloud size, we are going to give the highest energy level for the valence electrons. So the more electrons that are around the nucleus, the higher the n number will be. And the energy shell value, or the energy level, so you'll see both terms used, energy level, energy shell, is corresponding to the period for that element on the periodic table. So that means our values for n are always whole numbers. For our current periodic table, the highest number would be 7 because we only have 7 periods. But in theory, if we would discover a whole lot more elements, a whole lot more man-made elements, we could have n equal 8. Any whole number could be considered theoretically valid. Let's look at the periodic table to understand how we're going to find the n for an element. We're simply going to locate an element and then find out what period it is on the periodic table. So the n values would be 1, 2, 3, 4, 5, 6, 7, corresponding to the periods. And a reminder, this is a continuation of period 6 and 7, so n here would be 6 and 7 when we're looking at the n values. So what is n for iron? We find iron here, atomic number 26, so its n value would be 4 because it's in period 4. For uranium, its n value, it's in the actinide series, so it's in the 7th period, n would equal 7. It's that simple. Look at our next quantum number, the angular or sublevel subshell quantum number, represented by the letter L. And okay, we said it's a quantum number, but we are going to simplify things so that it isn't as confusing, and we are going to use letters to describe the shapes, S, P, D, F, G, H, and I. And those letters come from specific things in the wave functions, why they've chosen those particular alphabet letters. The GHI are in quotes because you will see as we go through, we haven't gotten that far. We don't have enough elements on our periodic table to need those shapes. And very simply, whatever shell level, energy shell level I'm on, that is how many subshells I have to have. So on level 1, we have 1 shape. Level 2, we have 2 shapes. Level 3, there are 3 shapes, etc. And what does that end up looking like? Something like this. So what we're saying is if I am on n equals 1, I'm going to have 1 sublevel or shape. And that shape would be S. We're going to go in order. So level 2, we have 2 shapes, S and P. Level 3, 3, SPD. Level 4, SPDF. Level 5 would have 5 shapes, etc. I think you see the pattern. Help people distinguish which level we're on when we're talking about, say, the S shape, since that shows up on every level. We're going to put a coefficient telling the energy level, and then we would put the shape. So that would be a 1s. We can see we have a 2s. This we would write as 2p. Then we'd have a 3s, 3p, 3d, etc. The next number is the magnetic moment or the orbital number. And this one is telling us the orientation, so sort of like that axis orientation. And remember, this is still within a probability map, not an exact spot. And as a result, when we're describing these orbital areas, we are ultimately going to tell you how many of a particular shape that we have. And where do these values come from? These very, very complex wave functions that Schrodinger developed. And at this point, it's very easy to see the pattern on how many orbitals we have for every shape, and that's going to be your focus, just seeing the pattern and counting those. So when we have the S shape, we only ever have one of them. For the P's, we have 3, the D's 5, but you can guess F's 7, and again, in theory, we would have 9, 11, and 13 for the other shapes, although, as I said earlier, you will see that we do not end up using them when we actually identify the quantum numbers for the different electrons. All right. Finally, we have the spin number. Spin number, easiest, there's only 2 possible values, and we said we have that because each orbital, and again, remember, think of it like a little home for the electron, the area where I'm most likely to find an electron. At most, we can have 2 electrons trying to occupy a spot because they're the same charge. They're going to try and get as far apart from each other as they're repelling, and we simply assign 2 values. You're either spinning positively or negatively. So that doesn't mean 1/2 as in 0.5 mathematically. It's directional. So we are saying 1 out of 2 electrons is spinning clockwise, and that is associated with the positive 1/2, and the negative 1/2 would be the electron that is spinning counterclockwise. So that's all we mean. Try to visualize a little of this all together. So I'm showing you the dense nucleus in the center, and then we have fuzzy lines that we're not thinking of them as fixed orbit paths, but they're orbitals. So we would represent our n value. We're going to show those numbers in red. So this would be n equals 1, n equals 2, n equals 3, n equals 4 as we move away from the nucleus. Our subshell numbers, we're going to use letters. I'm going to draw circles. So our S shape on level 1, we can only have one shape. So we have the S shape. On level 2, every S shape, we only have one. So we have one S shape. But remember, the p orbitals, we could have 3 of those. So we're going to draw 3 p orbitals on level 2. Then level 3, we have S, P, and D, so we'll have one S shape. Again, we'd have 3 P shapes, and then we will show 5 D shapes. And then finally, we have up to level 4 here. On level 4, we would have one S shape. We have P's. So we'd have 3 of those. 1, 2, 3. Our D's, we would have 5. And because we're on level 4, we have to have 4 shapes. So SPD, and the next shape would be F, and there would be 7 F's. So I'm going to draw 7 orbitals. 1, 2, 3, 4, 5, 6, 7. Right? Then finally, the spin numbers, I'm just going to show a couple of those. The spin number we would think of as within each orbital area that I can house 2 electrons, and they would be in opposite directions. So on this diagram, just to be very simple, I'm just going to make an X. So we'd have 2 electrons in there, 2 electrons in there, and each orbital could hold no more than 2 electrons. All right, so you may need to watch this video a couple times. I know it's hard, but the big thing that we want to understand and use these numbers for is to be able to do and draw what we call electron configurations, and that'll be the big idea that we want to be able to accomplish at the end of this chapter.